to talk about composite functions, and I'm going to jump in with these two functions. Let's let f of x equal 7x squared minus 1, and we'll let g of x equal 1 minus 6x. Now suppose we begin by just calculating this expression, the value of this expression, f of g of 4. Now when we know when we have an expression with multiple sets of parentheses, we start in the inside. So our first step would be to calculate g of 4. So I can come over here and do that, calculate that expression. So g of 4 is equal to 1 minus 6 times 4, or 1 minus 24, that's negative 23. So we know g of 4 is negative 23. Let's make that substitution for our g of 4 right here. So now we're looking for f of negative 23. So now we're substituting negative 23 into that first equation. Now, when we substitute it in, remember, when you make a substitution, I'm coming over here in my workspace, f of negative 23, you put negative 23 in, make sure you put it in parentheses, so you know it's going to become a positive value. So negative 23 squared, I'll just do that on my calculator. So we have 529, and we're multiplying that by 7, and we're subtracting 1. So we get 3,702. Now instead of writing the expression this way, because we have multiple set of parentheses, sometimes it's nicer if we write it with our composition notation. And we would write something equivalent to this as f composed with g of 4. And when we see this, we start here with g of 4 just like we did in the previous problem. Evaluate that expression and then find f of that expression. So we would do exactly the same thing. We'd have f of negative 23, and we would still end with that 3,702 value. So let's do another one. We'll just start with that composite notation. Let's talk about f composed with g of negative 1. So we're still going to use these same two equations, these same two functions. Let me box them up here so we know we're going to continue to use these. So when we begin, we start with g of negative 1. So let me come over here in my workspace, g of negative 1. I substitute negative 1 into the function, into that g function. So we have 1 plus 6, or 7. So that means we have calculated g of negative 1. So now we're going to find f of 7. We have just replaced that g of negative 1 with our 7. So now we find f of 7. So we have f of 7 is 7 times 7 squared minus 1. And again, we might find it handy to use our calculator for this one. And we get 342. In order in which we do our composition matters. For example, if we had done this problem instead, g composed with f of negative 1, my composition symbol there, it looks a little bit big. That really is about the size of a degree symbol in the middle of the line. It almost looks like an O there, and it should be a little bit smaller. That's not Goff, it's G composed with F of negative 1. So in this case, we start with the inner function, the one that is closest to the number first. So we would find f of negative 1 first. I'm over here in my workspace. So I would find f of negative 1, substituting that in. And do your evaluation of this expression. So we have negative 1 squared is 1 times 7 is 7 minus 1 is 6. So we've calculated this to be 6. So now we find g of 6. So I'm just working my way backwards. So I have g of 6. I pop 6 in here. And if you've worked with functions very much, you might be able to do that calculation in your head. 1 minus 6 times 6, right? So we have 1 minus 36. That is negative 35. So here's what I wanted you to notice. F composed with g of negative 1 and g composed with f of negative 1 gave us different values. Let's do another one. Let's work with a couple new functions. Let's use f of x equals the absolute value of x minus 10. And we'll just have g of x equal 10 over x. So here are our two functions. Let's calculate f composed with g of 2. So remember, we start with the function closest to our number here. So we'll start with g of 2. I'm going to do my calculation. It's 10 over 2. We substitute the 2 into our function. So we get 5. So now I know I'm talking about f of 5. And I can substitute 5 into my f function. I'm over here on my workspace. Absolute value of 5 minus 10. I hope you can see that that's negative 5. So I have negative 5 as my answer. We could do another one. Let's do g composed with f composed with f of 4. There's nothing that says we only can use two functions. We're using the same two functions, but we're using f twice. But I wanted you to see how it works. We're going to start with f of 4. We're going to evaluate that. We'll take f of the result and g of that result. So let's start here, f of 4. So pop 4 into the f function. Absolute value of 4 minus 10 is 4 minus 10 or negative 6. So this expression is negative 6. So now we have g composed with f of negative 6. And we evaluate that. So we start with our f of negative 6. We pop negative 6 in there. Take care to take the absolute value. So we have 6 minus 10. That's negative 4. So we have evaluated this and we now know it's negative 4. So now I'm at a g of negative 4. And we can substitute negative 4 into the g function. And we have 10 over negative 4, which we know we would reduce and have negative 5 halves. Let's do another problem. Let's let f of x equal 3x minus 1, and we'll let g of x equal 5x plus 9. Let's start with f composed with g of negative 3. So I hope you recognize where to start. We would start with our g of negative 3 first. Let's do that calculation. 5 times negative 3 plus 9. We have negative 15 plus 9, that's negative 6. So here's our negative 6 right here. So we're talking about f of negative 6. And we pop negative 6 into our f function. And we have 3 times negative 6 minus 1. And we have negative 19. Take care with your order of operations. Sometimes, though, instead of wanting f composed with g of negative 3 or f composed with g of 11, I want the brand new function that would be this, f composed with g of x. You see this expression, which represents the composition of these two functions. Let me remind you what this notation means. It means that we have f of g of x. I went back to our notation that looks like this. So this implies we're going to take the entire g function and substitute it into the f function. We're not looking for a number now, we're looking for a new function. So this entire g function is going to replace x in the f function. So our equation will look like this. 3 times, I'm going to replace the x with the 5x plus 9, and then minus 1. And now we simplify, so we have 15x plus 27 minus 1, and we have 15x plus 26. And we have the composite function, f composed with g of x. Now, let me point out, if you, at this point, suppose we hadn't already done this problem, and I now asked for f composed with g of negative 3. Instead of putting negative 3 into the g function and then the result into the f function, I could just put this negative 3 into our new composite function, 15 times negative 3 plus 26. And we have negative 45 plus 26, which is negative 19, the same result that we had over here. Now this would be handy if we needed to evaluate f composed with g of lots of values. It would be handy to have this composite function rather than having to take 2 steps every time to find the value. I mentioned before that the order matters. Suppose we found g composed with f of x. And now we want the, you know what, I'm going to do this on a separate piece of paper because I want a little more space. So let me write those two functions down again. We have f of x equals 3x minus 1, and we have g of x equals 5x plus 9. And the question is, again, here's the question we were going to or come up with, or the expression, or the new function. How about if I say it correctly? The new function we're trying to come up with is the composite function that is g composed with f of x. Now this time, the f is what we call the inner function, the one that's inside, closest to this variable here. It is going to be substituted into the g function. So let's make that substitution. So we have 5 times 3x minus 1 plus 9, and we have 15x minus 5 plus 9, and we have 15x plus 4. Remember, f composed with g of x was equal to 15x plus 26. Now we have g composed with f of x is 15x plus 4. So they did in fact were in fact different functions. So if I were now asked for g composed with f of 10 I don't need to go back to these functions. I have my composite function. I can just substitute 10 into that function. 15 times 10 plus 4. So we have 150 plus 4. And we have just used our composite function. Let's do another one. Let's let our function now be this. F of x equals x squared minus 3. And we'll let g of x equal 2x plus 5. Let's jump in and find f composed with g of x. So again, keep in mind our inner function is the g, so our g function will be substituted into our f function everywhere you see an x. So we would have, instead of x squared, we'd have 2x plus 5 squared minus 3. And generally we simplify, so I would square this binomial, so we get 4x squared plus 20x plus 25. Go to scratch paper if you need to do that calculation. Then we have minus 3, so we have 4x squared plus 20x plus 22. And it's done. And again, we could calculate or substitute in a value, f composed with g of 7 or f composed with g of 11 if we needed to. Let's do something else. I'd like you to see this. How about if we had f composed with f of x? So now we're going to take the f function, which is x squared minus 3, and substitute it in for the x in x squared minus 3. So here's our f function, x squared minus 3, and we're replacing the x with x squared minus 3. So it can be a little bit entertaining to compose a function with itself, but there isn't anything particularly different about this one. We square the binomial, so we have x to the 4th minus 6x squared plus 9, and we still have minus 3. And we have x to the 4th minus 6x squared plus 6. And we have just found f composed with f of x. Let's do another one. Suppose we had this function. It is f of x equals x plus 4 and g of x equals x squared plus 3x minus 50. And let's start with this one, f composed with g of x. I hope you see where we're headed. We've done a few. Do you know which function is being substituted into the other one? Right? Our g function is our inner function now, the one on the inside here. It's going to be substituted into the f function. So we replace x with g. So the entire g of x function is replacing x, and then we'll add the 4. So let's pop that in. So we have x squared plus 3x minus 50 plus 4. Doesn't take too much to simplify that. And it's done. A little more entertaining will be the composition in the other order. G composed with f of x. This time f is the inner function. And here's what I wanted you to notice, that there are 2 places where we'll have to substitute in the f function, because there are 2 places where we have an x in the g function. X plus 4 is being substituted in everywhere you see an x. So I have an x plus 4 squared plus 3 times another x plus 4, and then minus 50. And then we can do our simplifying. So we square the binomial. Again, go to scratch paper if you need to. Distribute the 3. And then we have some tidying up to do here. We have x squared plus 11x. And what do I have? 28 minus 50. Negative 22. And we have the composite function. Let's do another one. How about a function that looks like this? F of x equals the square root of x, and g of x equals 7x minus 2. I hope you can see where we would head with this if we wanted f composed with g of x. Notice our g function is the inner function this time. It's being substituted in for x. So we would have the square root of 7x minus 2. And there is nothing else to do to simplify it. You might notice that there is a restriction on the domain here, right? We would notice that for this particular function, that 7x minus 2 would need to be greater than or equal to 0. So for this composite function, we can only substitute in numbers or real numbers that are greater than or equal to 2/7. If we substituted in 0, we would have a negative number underneath the square root. And when I say that, I mean we're talking about real valued functions. When we're dealing with these functions, we're keeping it real. But I wanted to make another point with respect to this one. Notice that the 7x minus 2 got put into the square root function. You can see what it looks like. What if we wanted to reverse the process? Suppose, and this is actually an important idea that comes up in later classes. Suppose I had given you the function that h of x was equal to the square root of 7x minus 2, and I said I'd like you to come up with f of x and g of x so that f composed with g would equal that h function. Could you see how we would come up with that 7x minus 2 as the inner function and the square root of x as the outer function? Well, a little more obvious when the answer was right in front of you, but let's do another one. Suppose the problem were this, and the directions would say, find f and g so that f composed with g equals h. And you're going to be provided with an h function like h of x equals 3x minus 11 to the 4th power. So I'm looking for an f function and I'm looking for a g function. And the g function is our inner function. What got put into another function that would give you this h? Can you see that this 3x minus 11 got put inside parentheses, or we could think of it that way? So I could make my g function be 3x minus 11. But what did it get put into? Well, it had to be put into a function that would raise it to the 4th power. So I would just have f of x equals x to the 4th. And I have this function decomposed. And decomposing functions actually is something that's important in later classes. Let me mention that the decomposition of this is not unique. We could have done a different representation. Suppose, for example, that I had let g of x equal 3x. Because I could have. I could say, hey, this is the g function. So I'm thinking, okay, what did that get put into? Oh, it had to have been put into an x right here. So my f function could be x minus 11 to the 4th power. And you can confirm, you put that 3x in place of x, you will get this particular function. And in fact, there are an infinite number of possibilities for the way in which you could decompose this function. I think this one is probably the best one, but this one may be relevant at some point as well. Let's do another one where we're going to decompose the function. So the directions again will be find f and g so that f composed with g equals h. And this time I'm going to let h of x equal the cube root of x squared minus 2. So I'm going to write my f of x here and my g of x here. And you could pause the video and think about it. Do you see what might work? As our inner function, that x squared minus 2. But what did that x squared minus 2 get substituted into? That cube root function. So there's one way in which we could decompose it. Here's another way. What if we let g of x just be x squared? Can you see what f of x would need to be? That x squared would need to replace an x, but you'd still need a minus 2 over here. And let me just mention, I said on the previous problem there were an infinite number of ways, but I didn't actually give you an example. Let me give you another example to illustrate that point. Suppose I wanted g of x to equal, say, x squared plus 5. But I still need to be the result to be this. So I'm going to put this into a function where once I compose it, I get x squared minus 2. Well, if I let f of x equal the cube root of x, let's see, if I put x squared plus 5 in there, I better subtract 7. If I put x squared plus 5 in for x and subtract 7, I would still get this same value. So I have just decomposed this function h 3 different ways. And I'll tell you, this to me is just a fun little game. You could come up with, lots and lots of other ways in which you could decompose it. But as a practical matter, often your goal is to take a complex looking function and break it up into 2 simpler functions. And if you get too complicated or convoluted, then it sort of defeats the purpose of decomposing. Let's do one more. Let's decompose this function. Let's make it h of x equals 1 over x squared plus 23. Do you see a possible decomposition for this one? I hope you see it right here. This x squared plus 23 could be substituted into 1 over, and it's going to be put into the denominator. So we want the denominator to be just 1 over x. If somebody were asking me to decompose this particular function in the way that would be most useful, I would probably present it this way. But you could decompose it another way, perhaps x squared here. And do you see what the other function would be? How about 1 over x plus 23? So I hope you'll go practice composing functions and decomposing a few.